In this video, we're going to explore the graphs of polynomial functions, and we're going to look specifically at how we can transform polynomial functions. So on the screen here, you're going to see three polynomial parent functions. Now, I can't really include all of them in this particular video, but a polynomial parent function really is going to look like x to the power of some positive integer. So we're going to explore x to the third, fourth, and fifth, but you're going to need to be able to repeat this process for any polynomial parent function that you might be given. So think x to the sixth, x to the seventh. You would have to go through this exact same process. Now, in order to be successful with these, you do need to know how to generate a parent graph. So what I like to do is just write down a table with a couple of key values in it so that I kind of know what I'm going to be transforming later on. So again, these are the parent functions, and we're going to be transforming them. Now, in order to create an accurate graph of x to the power of 3, I'm just going to select values from -2 to 2 so that I can kind of get an idea of how this is going to work. So if I take -2 and I cube it, so that's -2 times -2, which is 4, times -2 again, I get -8. If I then take -1 and put it in here for x, I get -1 times -1 times -1. So -1 cubed is -1. 0 to the power of 3 is 0, because 0 times 0 times 0 is 0. And then 1 to the power of 3 is 1 times 1 times 1, which is 1. 2 to the power of 3 is 2 times 2 times 2, which 2 times 2 is 4, times 2 is 8. So if I plot a general graph here, so I have -2, -8, -1, -1, 0, 0, 1, 1, and 2, 8. You can see it kind of looks like a kind of weird squiggle graph. And what this is really going to look like is it's going to kind of look like an upside down parabola on this half. And then it's going to curve through 0, 0 and look like a right side up parabola here on the right. So that's what our x to the power of 3 function would look like. Now let's repeat this process with x to the power of 4. Now what I remember about anything to an even power is that anything to an even power is going to result in a positive value. So thinking about x is -2, -2 times -2 is 4, times -2 again is -8, that was x to the power of 3. Then if we take that -8 and we multiply it by -2 one more time to make it x to the power of 4, we get a positive 16. Then if we take -1 to the power of 4, that's -1 times itself 4 times. That's ultimately going to become a positive 1. Then 0 to the power of 4 is 0. 1 to the power of 4 is 1 times 1 times 1 times 1, which is 1. And 2 to the power of 4 is 2 times itself 4 times. 2 times 2 is 4, times a third 2 is 8, times a fourth 2 is 16. So here I don't quite have as many values to plot, so I can see this graph is getting a little bit steeper. So I have 0, 0, then I have 1, 1, and -1, 1. And then if I were to even just estimate 2, 16, so it'd be up 1, 2, 3, 2, 3, 4, 5, 6. I can see it's going to be somewhere up here. So it's a pretty steep graph here, and I'm just going to guesstimate that on the other side as well. So here it kind of looks like a parabola, but it's curving up at a steeper rate than a parabola did when we had x to the power of 2. So there you can see my x to the power of 4 graph. Then finally, hopefully you're starting to see the pattern here. If we did x to the power of 5, again, we would take all of these values, -2 to 2, and take them to the power of 5. If we do that with -2, we end up with -32. With -1, we end up with -1. Then we get 0, 1, and -32. So essentially, this x to the power of 5 graph looks pretty similar to the x to the power of 3 graph. It's just steeper and increasing and decreasing at steeper rates. So here, I mean, this one would curve super steeply because it's got to go all the way up to positive and -32 when it gets to x is 2 and -2. So hopefully this gives you a general idea of what your polynomial parent functions will look like, as we'll need to be able to generate parent functions in order to graph our transformations. So on the screen here, you're going to see the 5 different transformations that a polynomial can undergo. What's really cool about transformations in math class is that transformations apply, A, H, K, and B, all apply in the same way to all of the different types of graphs you could possibly transform. So what that means is everything that we learned previously about quadratic transformations, so all of the parabola transformations where we moved the graph left, right, up, and down, and we stretched it and we shrunk it, they work in the exact same way here. So we're not going to spend quite as much time on reviewing these concepts because there's something that we've already learned in this course. So I'm going to summarize them quick on this particular slide, and then we're going to jump in and we're going to apply them right away. So the first two that are important to know are the horizontal and vertical translations. Now, a translation is shifting or moving the graph around either left and right, up and down. Horizontal just moves the graph, some units to the left and to the right. And vertical moves a graph some units up and down. So we're going to see horizontal and vertical transformations. Now, hopefully you remember those values of h and k. H is the value that we put inside here, and this value inside, if we add or subtract a value from x, that value inside is going to shift the graph left or right. Something to remember about h is that it works the opposite of what we expect. So if we have a -6 inside of here, it's going to shift the graph in the positive horizontal direction to the right. If we see that we have a +4, it's going to shift it in the negative x direction or negative horizontal direction, which is to the left. So our horizontal translations is a number added or subtracted to the inside of the parentheses from x, and remember it works opposite of what we expect. Then our vertical translations are our k value being added on the outside. So remember we talked about outside and inside. Outside here is going to move that graph up and down. And this works just as expected. If we add a 5 on the outside, it's just going to take the parent graph and shift it up 5. If we subtract 3 on the outside, it's just going to take that parent graph and shift it down 3. So those are the first two you need to know, horizontal and vertical translations, just moving the graph around. So the next transformation that we're going to look at is the reflection. And a reflection can happen either horizontally or vertically. Just depends which axis we're flipping over. Now, when we're doing a reflection, we're essentially multiplying the function in some way by -1, either on the inside where x is or on the outside of the entire function. So any change on the inside, remember, is a horizontal change. So the multiplication of -1 on the inside of the parentheses here represents a horizontal reflection. And what's a little tricky here is the horizontal reflection is going to be from side to side. Notice that this would have to be over the y-axis. So horizontal reflection takes place over the y-axis, and it's going to be by multiplying the inside by -1. Then, if we look at multiplying the outside by a -1, that is our vertical reflection. And if we think about a vertical reflection, we're reflecting over a line up and down, which means we're reflecting over the x-axis. So if we want to do a vertical reflection, we multiply by -1 on the outside of the function. And if we want to do a horizontal reflection, we multiply by a -1 on the inside of that particular function. Finally, the last two transformations that we're going to look at are vertical and horizontal stretches and shrinks. Remember, these are the graphs that either shrink or stretch it vertically, which means we're going away from or getting closer to the x-axis, or stretch and shrink it horizontally, which means we're getting further away or closer to the y-axis. Now, a vertical stretch or shrink is going to happen here on the outside with this particular a value. So notice we're multiplying on the outside, hence why it is a vertical stretch or shrink. The other thing to note is that the a value tells you if it's going to shrink or stretch. If a's distance from 0, so I'm going to put absolute value around those to represent distance from 0. If a's distance from 0 is more than 1, this graph is going to stretch. It's going to get taller. And think about this as we're going to take the entire graph and multiply all of its heights by 2. Because vertically it's the height here. We're going to multiply all of its heights by 2. Well, if I took you and multiplied your height by 2, that would stretch you way up. Now, if our distance from 0 for a is greater than 0, but less than 1, so something like a third or a half, that is going to be a shrink. Because if you think about it vertically, if I took your height and multiplied it by a half, you would shrink and get shorter. So you can see a couple of examples over here. If we multiply by a third outside of the parentheses, we're going to vertically shrink that graph by a third. But if we multiply it by something like 2, we're going to stretch the graph up by a factor of 2. Then finally, if we look at the horizontal stretches and shrinks, our b value here is something that we have to find. If you remember previously, the b value that we're multiplying by inside of the parentheses helps us to find how we're changing that graph. It's not the exact change. So that part's a little bit tricky when it comes to horizontal stretches and shrinks. So here, to give you an example, you can notice in here that our b value is equal to 2. You can see that very clearly in there. Now, because our b value is equal to 2, to find our factor, you can see b equals 1 over factor, we would say, okay, our b value is 2, that equals 1 over whatever our factor is. Maybe I'll call it x. And then this is something that I would need to solve. So I would just turn it into a fraction equals a fraction. So 2 over 1 equals 1 over x. If I cross multiply here, I get 2x is equal to 1. Divide by 2, and I find that x is equal to a half. The other way you can go about this process is b and the factor are what are called reciprocals of each other. So if you know that your b value is 2 over 1, which we can see in this particular example, you know that your factor is going to be that flipped over. So that's going to be 1 over 2. So that's the other way you can find your factor. Now, once you have your factor tells you if your graph is going to be stretched horizontally, so pulled further from the y-axis, or if it's going to shrink horizontally, so pushed closer to the y-axis. If you look at your factor, so make sure you look at your factor here. If your factor's distance from 0 is more than 1 unit, so in this case this would be like here, my factor is 3. If your factor's distance from 0 is more than 1 unit, that is considered a stretch. If your factor's distance from 0 is more than 0 but less than 1, so for example, the half we have here, this is going to be a horizontal shrink. So for the example that we see on the screen here, we're going to take the parent function, which if I write down the table for this particular parent function, so I have -2, -1, 0, 1, and 2, and I know my y values for x to the power of 3 are -8, -1, 0, 1, and 8. So that's my parent function. And you can sketch that out if you want in orange. That's perfectly fine. And this particular graph is going to be transformed to become g of x here. So we've made some changes here to g of x, and we have to decide what changes we have made. So what I like to do is off to the side, I like to write down, okay, did I change a, b, h, or k? And then I look at the equation and I decide which values I'm seeing so I can determine if I have stretches and shrinks or some translations or what is going on. So just by looking at this equation, I can see that I'm using two values. I can see that I'm adding a value on the inside, so that's my h value, and I'm adding a value on the outside, that's my k value. So I'm making some translation changes here. I can also see that a and b aren't used because I'm not multiplying this function on the outside or inside by any particular value. So I can see that my h is the value that's being added here on the inside, and I know that h works the opposite of what I expect. So this is telling me that I'm going to move the graph to the right in the positive direction 5 units. Well, I know that I'm moving to the right 5 units, which means x is going to add 5 because x is my horizontal movement, and I'm going to actually translate that and move it to the right 5. So I'm going to note here that I have to add 5 to my x value. Then from here I notice that I'm adding 2 on the outside, so that's my k value, that's my vertical translation, and that tells me I'm going to move the graph up 2 units. So what I know from there is that I'm taking all of my y values and I'm adding 2. So if I take my parent function table and I follow through with these, So here I'm going to call it my child function, which is g of x. It's my translated one. So I have, okay, my x's and my y values. Well, my x values, I'm adding 5 to all of those, so that becomes 3, 4, 5, 6, 7. Those are all my x values. And then all of my y values, I can see I'm adding 2 to. So I have negative 6, 1, 2, 3, 10. So now if I take those values and go over to my graph and plot them, I have x is 3, y is negative 6. So I can plot that. Then I have x is 4, y is 1, x is 5, y is 2, x is 6, y is 3, and x is 7, y is 10. So I can see that same squiggle that the x cubed parent function graph had, but it moved to the right 5 and up 2, which is exactly what I expected from these changes. So then I draw a little sketch, and there we have it. So let's go through the same process with this second example. So I can see my parent function is x to the power of 4. So if I write out my table here, that becomes 16, 1, 0, 1, 16. That's my parent function. Then I take a look here at my function and I think, okay, am I changing a, b, h, or k? Well, I only notice one number in this problem, and it's a multiplication on the outside. So I can see that I have an a value on the outside that is equal to a negative 1/4. And this value of negative 1/4, remember the negative part of that is going to be a vertical reflection. So that's going to flip over the x-axis. And then I am shrinking the graph by 1/4. So I'm making it 1/4 as tall. So this a value of negative 1/4 is going to vertically reflect it, and it's going to vertically shrink that particular function down to about 1/4 of its height. So what I do here is I notice that my a value is a vertical shrink and a reflection, but we can do this all in one shot. So because it's a vertical shrink, vertical changes happen to the y values. And because this is multiplying by negative 1/2 on the outside, we're going to multiply our y values by negative 1/4. So if we take a look at this particular function and we look at our y values, we're going to change them according to our a value. And we're going to leave our x values alone because as far as we can see, our x values, or our horizontal values, don't have any changes. So this is my child function, this is my g of x function. My x values, as I said before, stay the same because there are no changes horizontally to this graph, but vertically I need to flip it and shrink it. So I'm going to multiply each of these y values by negative 1/4. So 16 times negative 1/4 is negative 4. 1 times negative 1/4 is negative 1/4. 0 times that is 0, and then if I keep repeating, that is my new table for my transformed function. So I go to negative 2, negative 4, negative 1, negative 1/4. I'm going to have to estimate there. It's about right there. 0, 0, 1, negative 1/4, and 2, negative 4. So I can see that this graph got shrunk way down. And there is an approximation of what my sketch for this transformed graph would look like. And I can see that it fits my predictions of a vertical shrink, so it got shrunk down from its original graph, and it vertically flipped over the x-axis. So let's take a look at this final example here. Let's start by creating our parent graph. So we have x is negative 2 to 2, and we're going to take those all to the power of 5, so we get negative 32, negative 1, 0, 1, and 32. Then from here, we need to decide, are we changing the values of a, b, h, and or k? Well, if I take a look at this, what I notice is that I'm subtracting a 2 value on the outside. Subtracting a 2 value on the outside is going to vertically move the graph down 2 values, so I know that I'm changing k. I then can also see that I'm multiplying by 3 on the inside here. Multiplying by 3 on the inside here deals with my b value, and 3 is my b value, so then to figure out how my graph is changing, I take the reciprocal of my b value, which becomes 1/3. So what's really happening here is I am shrinking my graph by a factor of 1/3. And because this is on the inside, this is a horizontal shrink, and it's going to be applied to my x values. So what I need to do here is I need to do these one at a time. And when you have a mixture of translations and stretches and shrinks, you always start with the stretches and shrinks and the reflections first, because order of operations says multiplication comes first. So we're going to deal with the multiplication process of this first. So what we're going to do here is we're going to multiply all of our x values by 1/3, because we're going to shrink it horizontally by a factor of 1/3. So if I take all of these points and I shrink them down, so all of these x coordinates, because it's a horizontal shrink, that becomes -2/3, -1/3, 0, 1/3, and 2/3. Then from here, I also notice that I have a vertical translation that I need to apply. That's this going down by 2. So now I'm going to take my y values, which didn't change after that last one, so they're currently still at -32, -1, 0, 1, and 32. And what I'm going to do here is I'm going to move them all down 2 by subtracting 2 from all of these y values. So from here, if I do that, I end up with -34, -3, -2, -1, and 30. So I can now see the changes that have taken place on my graph. I can see that I have horizontally shrunk down my x values here, and I can also see that I have moved my graph down completely 2 units. So I'm going to now go to my graph and plot and do my best. I know there's a lot of fractions here. So I have -2/3 and -34. That doesn't quite fit on my graph. But I have -1/3 for x and -3. That's going to fall about right there. Then I have 0 and -2. So that's about right there. And then I have 1/3 and -1. So that's about right there. Then 2/3 will go all the way up to 30. So what I can see is this has gotten super skinny here. I don't really have a lot of great room to write. I can see it's super skinny, and that 2/3 and -2/3 are hitting pretty high. So we now have a sketch of our graph. We can see that we shrunk it horizontally by a factor of 1/3, and we moved it down 2 units.